Hello, Missy Mary, Kyrios ke Kyri. Good midday, ladies and gentlemen. I'd like to thank Professor Andy Gregory for organizing the Ancient Science Conference at the University of London this February 2023, and for the honor of being invited to give a keynote presentation, which affords me the opportunity to have a longer platform to present my ideas and research. Today, I propose to review the Greek discovery of incommensurability by attempting to resituate the early Greek philosophers in their historical, cultural, and most importantly, technological context. I'd like to begin by looking at an archaeological artifact. Ulrich Schadler in 2004 published these results, and he found in the Temple of Artemis in Ephesus, Temple B, which dates more or less to 625 BCE, the last quarter of the 7th century, more or less contemporaneous with when Thales was born, that on the one hand, burnt in a fire, he found this fragment, which he came to realize was the instructions for making this curve on this roof, a roof leaf. Along the sides of the Temple of Artemis in Ephesus, in order to protect the wooden column capitals and the wooden columns, these leaves were made, and the leaves have concentric circles on it, and this was found, which he then inferred was the instructions for the masons to make that curve. Now, when he looked at it more closely, what he discovered was that here we had a geometrical diagram, mathematically precise. The radius of the circle is 5.2 centimeters, which is 1/10 of an ionic cubit, and thus the circles in the drawing that have been defined by the sketch match the circles on the tile. Now, I begin with this to make 2 points. That in Thales' backyard, more or less, coming from Miletus, this is Ephesus, the architects were customarily making routinely geometrical diagrams that were mathematically precise. And given this, there can be no doubt that Thales and Anaximander were making geometrical diagrams. The earliest of the Greek philosophers were making geometrical diagrams mathematically precise. Now, the mathematical precision helps to make the point that when the architects are planning a temple and they plan it in a small model, and then they imagine it on gigantic scale, in order to be sure that the aesthetic sensibilities, the relation between the column width and the column height, the size of the column capital to the column shaft, the entablature and upper orders of the Ionic architecture, like the architrave, the pediment and frieze, and the lower architectural elements like the width and length of the stylobate, the distance between the columns, all had to be scaled up in proportions. And I'm emphasizing this because the theory of proportions was already practically applied, at least at the time of the birth of Thales. And so the theory of proportions discussed with by historians of mathematics need to take these considerations into their deliberations about understanding the earliest stages of the development of Greek geometry. Now, Thales is credited with making a measurement of the height of the pyramid when the shadow was equal to its height. And what we have here in the lower side of the illustration is a gnomon, of a vertical rod, and its shadow, to which Thales has access. And when that shadow is equal to its height, that's the time of day when every shadow, every vertical object casts a shadow equal to its height. And that's a time to make the measurement, when shadow equals height. Now, the experiment, it so happens, is more complicated than this, and I've discussed this in my book, The Metaphysics of the Pythagorean Theorem, Chapter 2. But now I want to make this point that in order to understand the Greek concept of ratios and proportional thinking, we need to understand that the ratio is to ask, how many of the little world of gnomon and shadow scale up to make the big world? So that we then think of this gnomon and shadow scaling up, and then finally fitting the whole image. And so I can then make the point that for the Greeks, a ratio is implicitly a comparison of all the potential multiples of one magnitude to all the potential multiples of the other. The Greek concept of ratio applied to this case is to determine how many copies of the smaller we can fit into the larger. Thales creates a kind of ladder to ascend to the top of the pyramid. Thales reckons the height of the pyramid by the number of measurable smaller units of gnomon and shadow that would fit inside the larger pyramid and shadow scaled up. His reasoning supposes that the gnomon height and shadow are the common measure of the pyramid height and shadow. Thus, we have evidence from the last quarter of the 7th century from the Temple of Artemis at Ephesus of geometrical diagrams mathematically exact. There can be no doubt that Thales was making geometrical diagrams, as we're going to go on to consider and explore. In monumental architecture, the diagrams displayed the theories of proportions. From a likely small model, all the architectural elements would need to be scaled up precisely to display the planned aesthetic relations between the parts. To do so, we begin with a common measure. In Ionic architecture of the 6th century BCE, it's column diameter, a theme I'll return to later in the presentation. But in the wooden architecture of the Artemisian B, circa 625 BCE, the end of the 7th century, the common measure might have been reckoned simply in cubits. From these procedures, we can see microcosmic, macrocosmic reasoning. The big world was scaled up from the little world. Now, let's think this through. The big world, like the height of the pyramid, was inaccessible, and yet was inferable from the little world because both were presumed to share the same structure. The geometrical diagram, because of its practical application, came to acquire a metaphysical meaning, because, though the diagram was unchanging, it nevertheless illuminated things about the changing world. The underlying presupposition that the little world would scale up in whole integers to fill the big world is the idea of commensurability. The beauty of the cosmos was encapsulated in the ratio thinking of commensurability. The discovery of incommensurability required a repositioning of this thinking, and we're going to look at this in detail as I try to unfold the theme today. Now, Thales and Anaximander made geometrical diagrams to discuss their various theoretical mathematical ideas. The early developments did not happen, in my estimation, as I've argued in earlier publications, in a math seminar, but rather in ongoing exchanges with compatriots who discuss metaphysical, mathematical, and practical issues. Geometrical diagrams, contra Netz, Reviel Netz, in his book, The Shaping of Deduction in the Greek Mathematics, against his view, I'm arguing that geometrical diagrams originated and developed with practical diagrams. Now, epistemologically, this means that abstract and speculative thought springboard from our embodied experience, not rejecting or transcending it. And this is why technological context is both relevant and important. The diagram offered a non-changing platform that illuminated the material world. It revealed a non-changing structure underlying change by means of which we could understand the changing world. This non-changing underlying ideal is just the sort of substance monism that Aristotle attributes to Thales, Anaximenes, Heraclitus, and Hippasus, and I'm going to say more about substance monism shortly. So this new study follows upon my long-standing work of resituating the early Greek philosophers in their technological context to see if we can gain new insights into what they thought and how they thought about it. I've been arguing, contrary to some of our distinguished colleagues, such as Chernus, Graham, Sassi, and Rossetti, that Aristotle's report at Metaphysics 983b and following about the early philosophers being source and substance monists is likely spot on. His report is plausibly from a summary by Hippias of Elis, in this case proposed by Snell, echoed later by Klassen, has been presented most elegantly by Dmitry Panchenko. Aristotle's report invited us to accept the claim that the early philosophers posited a single underlying unity, a persisting one under many. Thales called it water, Anaximenes air, and Heraclitus and Hippasus fire, that altered without changing, since the underlying nature or unity never perished. The critics have argued for various reasons that attributing substance monism, that is a persisting one under many that alters without changing, to the early philosophers is historically inappropriate and anachronistic. I hope you can see that this is not a small point, for if Aristotle's report in this case is accurate, then some of our distinguished colleagues have missed what is central to the origins of Greek philosophy. Aristotle's report, then, that the early philosophers were substance monists amounts to the claim that they were modular thinkers. The underlying module is subject to qualitative change, whether it's water, air, or fire. At one moment, of course, as we can see, appearance of things are hard as stone. At other moments, we have the fire at the stove, yet again, invisible when we breathe air, and then flowing liquid in a cup, but always remains the same module, always persists because it never perishes. Now, I've been arguing that Thales' investigations in geometry are connected to his metaphysical speculations that led him to propose that water was the underlying unity that altered without changing. This connection between geometry and metaphysics I describe as the lost narrative. If we place the diagrams for the geometrical propositions which with Thales is credited, alongside the diagrams or picturing that seem would have certainly burgeoned in his mind when he, or really anyone, measured the height of a pyramid or distance of a ship at sea, you will see that almost all of them concern right triangles and similar right triangles. Please note, positing the underlying unity as the right triangle, which is an argument I'm going to make for Thales and Pythagoras and the Pythagoreans, is a commitment to modular thinking. Now, here we have the diagrams. On this level, we have the familiar diagram for the theorem that when straight lines intersect, they make the opposite angles equal. Thales is credited with that. Thales is credited with this one, that if two sides of a triangle are equal, isosceles triangle, then the angles opposite the equal-sided are also equal. Third, that a circle is bisected by its diameter, it's literally cut in two into two equal portions, and that, as I've explained in earlier publications, that on the diameter of the circle, every triangle inscribed starting from one end of the diameter, touching the circumference and reaching the other end, is a right triangle. And this is going to be most central to the arguments I'm going to be advancing later in this presentation. For the proof of that, it's contained in these two diagrams. For the isosceles triangle and the scalene triangle, the angle at A has to be proven to be a right angle. Now, when he measured the height of the pyramid when the shadow equals the height, or when he measured the height of the pyramid when the shadow was unequal but proportional, he reasoned shadow length was to gnomon height, as pyramid length was to pyramid height, whether it was unequal or equal. This is an argument by similar right triangles. Had he measured the distance to the ship at sea, where the ship is out here and I'm standing here, My students are along the coast holding a rope. And then we take this line inward to sight the ship. It's argument by similar right triangles. And had he made the measurement from a raised tower, he then would have treated the raised tower as if it was a gnomon, a vertical rod, and then the distance would have been reckoned in terms of similar right triangles. Of all the 6 surviving illustrations, diagrams of Euclid from the medieval manuscripts, the oldest one that survived, dated to the 9th century ACE, 5 of the 6 show this diagram for the proof of the Pythagorean theorem. Notice there are no figures at all drawn on the sides, no squares or any other figures. And I believe that this diagram may well go back to Thales, which I'm going to connect to this diagram here. We'll have to wait for that. Now, can we connect Thales to a view that the triangle is the fundamental geometrical figure? I think we can, but it's got to be a speculative and hypothetical case. Proclus, on the authority of Eudemus, tells us that Thales went to Egypt and introduced geometry into Greece. Herodotus tells us that the Greeks learned geometry from the land surveyors in Egypt. Now, here's the story Herodotus relates in Book 2 of his histories. He relates the story that the Egyptian king divided the land into square plots, and if any portion of the arable land was robbed due to the Nile flooding, he would send the surveyors and diminish the tax consequences for that person by subtracting from the square area the portion that was no longer usable. Geometrically, how could this have been achieved? I've never seen anybody tackle this problem. But let's be clear that when the Nile had turgid flooding waters, the most likely place for it to be affecting your plot of land was if your plot was directly along the bank of the Nile. And if that plot was washed away, some part of it, it didn't get washed away in straight lines. So when the land at the edge of the Nile was washed away by the flood, the surveyors would have had to determine how much of the square plot was missing. Naturally, a flood will not wash away land in straight lines. So how did the land surveyors determine the area of robbed land? If one supposes that space is constituted by flat surfaces, all figures reduce to triangles. Now, what was the Egyptian evidence for this? I was stunned, having studied the Rhind mathematical papyrus, which dates at least to the time of the Middle Kingdom, which relates to Herodotus' story that Sesostris, who was a king in the Middle Kingdom, divided the land into square plots, and this probably goes back earlier. The problem number 51 deals with determining the area of a triangular plot of land. Not a triangle, a triangular plot of land. And so it seems to me the piece of land that had been ripped away, washed away, would be calculated in terms of small, medium, and large triangles. And the sum of the area of those triangular pieces would be subtracted from the total square area to determine the diminishment of the plot of land on which the tax in the form of tribute of crops would have to be paid to the king. So Thales could have learned or confirmed from the Egyptian surveyors that all figures reduced to triangles. Now, whether or not he made the next step from them or by himself it is not important, but I'm going to argue that he did. He came to see not only was the triangle the basic building block, but he looked inside every triangle and he could see that inside every triangle were 2 right triangles. And that was that the right triangle is the fundamental geometrical figure. Now we have the claim by Theon of Smyrna that the Pythagoreans divided all rectilinear figures into triangles. And as I'm going to go to show, that the triangle was seen to be the basic building block of the cosmos, and that if you had that view, you looked inside and saw that there were right triangles inside every triangle. And then the line of thought I'm encouraging you to take is that if you held such a view, you would keep on looking inside the right triangles to see if there was anything more to discover. Now I'd like to invoke a distinction, which I'm going to be using later in terms of the proof for incommensurability. But at the same time, it's a particular case that is going to help me work out the geometrical knowledge of Thales. I want to distinguish between visualization and a proof. And I'm going to show you this by considering that the angles of every triangle sum to 2 right angles. Now, according to reports by Proclus and Geminus, that while the Pythagoreans proved that the angles of every triangle sum to 2 right angles, hoi archeoi, that is the ancient ones, who could only be Thales or members of his generation, theorized, the Greek term is theoresanton. They theorized how the angles of every species of triangle sum to 2 right angles, equilateral, isosceles, and scalene. So let me show you the proof. In Proclus, on his commentary on the first 6 books of Euclid, of which the only thing that survives is the first book, we have this diagram. Now, this diagram is going to show you the Pythagorean proof. I'm showing it to you now. We start with a line, and then we make it perpendicular. And you can see that in every line, sometimes called a straight angle, there are 2 right angles. Now, it doesn't matter which direction you're going to make this line. It divides it into alpha and beta, and they sum, as this diagram shows, into 2 right angles. Now, let's take this diagram and extend the line, and then see that if alpha and beta are 2 right angles, and beta and alpha is a straight line, 2 right angles, and alpha and beta are 2 right angles, then we can see that opposite angles are equal. That's one of the theorems for which Thales is credited. Now let's continue this line through another parallel straight line. And now you can see, since alpha and beta equal 2 right angles and beta and alpha equal 2 right angles, alpha and beta also will equal 2 right angles. And so by making this diagram, we can see that beta is the same angle as beta. These 2 angles are equal. Now I'm going to take this line and I'm going to put it in this direction and show you that alpha equals alpha. That is, alpha equals here, that alpha equals alpha, except I'm turning the line around. And so we finally have the diagram in Proclus. And here's how it works. Alpha plus beta plus gamma equals 2 right angles. And this angle alpha is equal to this angle alpha, and this angle beta is equal to this angle beta. And if alpha, beta, gamma is 2 right angles, and alpha, beta, gamma inside the triangle equals 2 right angles. That's the proof that every triangle has angles that sum to 2 right angles. But according to Geminus, in Eutychius's commentary on Apollonius's Comica, the ancients theorized how the angles of every species of triangle sum to 2 right angles. Now, it could have been done in many ways. Let me propose a way that makes a lot of sense to me how it could have been done. We start with an equilateral, an isosceles, and a scalene triangle. Now, by dropping a cathetos, or perpendicular, you can see that inside this triangle are 2 right triangles. Drop a perpendicular, and you can see that inside this triangle are 2 right triangles. And also the scalene, inside every triangle are 2 right triangles. Now, here's how we reasoned that the sum of the angles sum to 2 right angles. He now is going to complete the rectangle, making this half triangle equal, if there are 4 right angles in every rectangle, then this half triangle equals 2 right angles. And now he's going to complete this rectangle. And there's 4 rectangles in every rectangle, 4 right angles in every rectangle. And this half triangle is 2 right angles. So if there's 2 right angles in this one, and there's 2 right angles in this one, now it looks like there's 4 right angles in this triangle. But if you subtract these two right angles, you see that this plus this equals two right angles. Let's watch that again. You complete the rectangle, and you know in a rectangle there are four right angles. This triangular half equals its half, so it's two right angles. Complete the rectangle, which has four right angles, and this triangle, which has half the area, is two right angles. So if there are four total right angles and you subtract these two, then there are two right angles in this triangle. And so we see it one more time. There are four right angles in every species of triangle. This triangle is half the size of this four right angles. There's two right angles. This has four right angles. This triangle here has half the angles of this. And then one can see that two right angles and two right angles are four minus these two. There's two right angles in every species of triangle. Now, Plato's Timaeus, in my estimation and my argument in the Metaphysics of the Pythagorean Theorem book, is that Plato's Timaeus preserves this Pythagorean story, which I say goes back to Thales. And it leads to the thesis of building the cosmos out of right triangles, because the right triangle is shown to be the fundamental geometrical figure. Here's what Plato says, has Timaeus of Locri of southern Italy. Now, Timaeus comes from a place that could have been influenced by Empedocles or Alcmaeon or Pythagoras and the Pythagoreans. But there's nothing of Alcmaeon or Empedocles in this story. This is purely the kind of story that Pythagoreans told. In the first place, then, it's of course obvious to anyone that fire, earth, water, and air are bodies, and all bodies have volume, bathos, and volume, moreover, must be bounded by a surface, epipedon, and every surface that's rectilinear is composed of triangles. Now, all triangles are derived from two right triangles, each having one right angle and the other acute. This we assume as the first beginning of fire and the other bodies, following the account that combines likelihood with necessity. And from that analysis, Timaeus, in Plato's dialogue, will go on to explain the construction of the cosmos out of right triangles. Now, I've never seen this in diagrams, so let's take a look at it in diagrams. All bodies have surfaces, so if we begin with any figure, straight line figure, you can see that it can be divided into triangles. And we've already considered that no matter what kind of triangle it is, every triangle has inside of it two right angle triangles. Now, inside either the isosceles right triangle or the scalene right triangle, there are no equilateral right triangles. You can see that this isosceles right triangle, the right angle is at A, is now, if I now just turn it around, that's the big guy. And these two parts are the similar right triangles of which it's made. And here, the scalene right triangle, there's the big guy. And these are the two unequal parts, similar right triangles, into which it's divided. And if we continue to divide each of them from the right angle, we'll see that each will divide epapiron forever into two similar right triangles, into two similar right triangles, into two similar right triangles ad infinitum. Now, what happened in the Timaeus, and I believe this goes back to Pythagoras and the Pythagoreans, as I'm going to go on to relate. The next question was, how many regular triangles, squares, and pentagons, or any other figure, can you place around a point that will still fold up? And the result was that from four triangles, you could make the pyramid. From 8, you could make the octahedron. From 20, you could make the icosahedron. And from 6, you could make the hexagon. In short, the 4 elements are fire, air, water, and earth. And we need to consider then this. the lines of thought at Timaeus 53c are ones that lead to the Pythagorean theorem at 631 in Euclid. It's the version of the proof that shows the right triangle is the fundamental geometrical figure. What was the proof that all figures reduce to triangles and further to right triangles? My argument in the metaphysics of the Pythagorean theorem was to show that the lines of thought that led exactly to the discovery of the Pythagorean theorem, so that there's a metaphysical meaning of that proof of the Pythagorean theorem. Now, my next step is to show how Thales discovered that every right triangle inscribed in this semicircle on the diameter is a right-angled triangle. And then I need to show you why he does so. We have this report in Diogenes Laertius that Pamphila, the mathematician, states that having learned geometry from the Egyptians, Thales was the first to inscribe a right-angled triangle in a circle, whereupon he sacrificed an ox. Others tell this tale of Pythagoras, amongst them Apollodorus the arithmetician. Now, it's my claim to understand this testimony that this is not a confusion or didography, but rather it's plausible that Pythagoras followed through using the same diagram as Thales. Now, why is Thales trying to inscribe a right triangle in a circle? Because, in my estimation, he believes that all rectilinear figures reduce to triangles, and inside every triangle are right triangles, and the right triangle is the building block of all appearances. And so it may have been objected by one of his compatriots. Well, that's all well and good for straight line figures if you think space is flat, and all figures are made of these straight lines and then are folded up into volumes out of which the cosmos is made. But how about the circle? That's not constructed out of right triangles, is it, Thales? And quite amazingly, the answer is yes. That is, if you start with a semicircle and you realize that this angle, which I'm going to go on to show you how he proved this, starting from one end of the diameter, touching the circle and going to the other end, that's a right angle. And then this is a right angle. And then that's a right angle. And from that, he came to understand that if you made all the possible right-angled triangles in this semicircle and filled out the circle, you would see that the circle itself is built out of right triangles. And I believe that one way to understand this sacrificing of the ox, the great sacrifice, is he realized, yes, this finally showed that all figures are built out of right triangles. Now, what's the proof? How does Thales know this? Well, it's my argument he always began with the isosceles right triangle. And here the problem is to prove that angle A is a right angle. Now note, we have this line AD and BD, which are both radii of the circle, so they must be equal in length. And AD and DC are both radii of the circle, so they're equal in length. And Thales was credited, you may remember, with the theorem that if two sides of a triangle are equal length, then the angle opposite each side must be equal. And if there are two right angles in every species of triangle, and there's a right angle here, then angle A and angle A must each be half of a right angle. And the argument will be ceteris paribus the same. AD and DC are of equal length. And so the angles opposite them must be equal. And if there are two right angles in every species of triangle, and this is a right angle, then beta and beta must be half a right angle each. And if alpha is half a right angle and beta is half a right angle, then alpha, this angle at A, is a right angle. That's the first part of the proof. Now it holds for the isosceles right triangle, which the areal equivalence is immediately obvious. But does it also hold for the scalene? And the argument is the same. AD and BD are both radii of the circle, so this angle and this angle must be equal. And AD and DC are both radii of this circle, so angle B and B must be equal. And so we have angle A, angle B, and AB which equal two right angles. And if you divide by AB, then AB must be a right angle. And that's how he knows that all triangles inscribed in a circle on its diameter are right angle. And this affords two things. One, it allows him to be sure that when he's looking at diagrams, he can be sure he's got a right angle triangle by having a circle with a compass and a straight edge, and then now exploring further the right angle triangles, because he knows the right angle triangle is the basic building block. And now he's going to look inside to see what more he can discover. Now, what he discovers in the next step is this, the mean proportion. We start again with this isosceles right triangle, and here's what he's going to realize, that alpha A is to B as B is to C. That's a continuous proportion. And what he realized was that the square on B is going to equal the rectangle made by these two parts. So that square is going to equal this length with that width. He sees this as immediately obvious. Now, is he able to see this mean proportional relation in the scalene triangle? He begins this way, and I'm arguing, yes, he did. He can see that the square on this is equal to the rectangle made by this length and that width. But he does not have the way to prove it geometrically. That had to wait for the Pythagoreans in Euclid, which is now preserved in Euclid Book 2, the shortest of all of the books, the last theorem, Theorem 13, which proves how you can make a rectangle equal to a square. But this is a mean proportion. This is a pattern he saw in the right triangle. And so let's go over that again. The mese analogos, he can see that a square on B equals the rectangle made by the two parts into which the hypotenuse is partitioned. And with regard to the scalene, he can see that the square on B, though it's gotten smaller, is now equal to the rectangle made by BD and DC. Now, it's my contention that once he knows that the right triangle is the basic building block. He looks inside and he sees this mean proportional relation. And then he asks, are there any other mean proportional relations? And I'm claiming, I'm arguing, yes, he saw it, and I'll show you how. He always begins with the isosceles right triangle because aerial equivalences are immediately obvious. Now he makes a square on AC. He's going to now look at the relation as BC is to AC, so AC is to DC. That would mean the square on AC is equal to the rectangle made by this length, which is going to go down this way, and this width this way. So first, let's fill in the square. And you can see that this piece equals this piece, and this piece has 4 equal pieces. And now we make this rectangle, and you can see since this piece here is equal to this, these 4 pieces are equal to these 4 pieces. And then he looked at the other side, and he saw that now it's the relation between BC is to AB as AB is to BD, another mean proportional relation inside. And that is one of the lines of proof to the Pythagorean theorem on the presupposition that the right triangle is the basic building block of the cosmos. And then he looked at it in terms of the scalene right triangle, and he had to do it empirically with ruler and compass because he didn't have the geometry yet to finish it, but he could see and empirically test to see that this relation was exactly this relation. That the square on this hypotenuse was equal to this rectangle, and this square on that hypotenuse was equal to this rectangle, and that the square on the hypotenuse BC was equal to the sum of the two squares. Now we're ready to get to the discovery of incommensurability. We have 3 paths to follow, it seems to me. 1, the Pythagoreans explored ratios, the relations between side and diagonal of a square, sometime in the 5th century BCE. Some propose as early as 500 BCE. It's a position I'm going to argue for, or soon after. Others, it wasn't until the mid-5th century, and still others, the last quarter of the 5th century. And this proof relied on a knowledge of the Pythagorean theorem. And so wherever you place it, if you follow that line of reasoning, the Pythagorean theorem had to been known before it. There's a second hypothesis, which is proposed by Wilbur Noor, that the Pythagoreans proved incommensurability along the lines later preserved in Plato's Meno, and that line of reasoning does not presuppose a knowledge of the Pythagorean theorem. And thirdly, there's the line of thought that Hippasus of Metapontum, the Pythagorean from southern Italy, where Pythagoras moved to not later than 520 BCE, plausibly made this discovery while investigating the construction of the dodecahedron. And the dodecahedron, which is one of the building blocks of the cosmos shown in Plato's Republic, that is, it's the whole all into which the 4 elements are inscribed, that is composed of regular pentagons. And so we'll have to look at an understanding of the regular pentagon. Now, I'm persuaded of the likelihood that Hippasus made the discovery visualizing incommensurability with the regular pentagon, and later proved it with the diagonal of the side of a square. That's why I took the time to make clear the difference between the visualization that there were 2 right angles in every species of triangle, and the proof that's the one preserved for the Pythagoreans by Proclus. Now, let me turn just briefly to just remind you that the Pythagoreans are credited with certain theorems of numbers preserved in Euclid in Book 9. So, for instance, 921, the sum of even numbers is even. So 4 plus 6 is 10. The sum of an even number of odd numbers is even. 3 plus 5 plus 7 plus 9 equals 24. The sum of an odd number of odd numbers is odd. 3 plus 5 plus 7 is 15. An even number minus an even number is even. 12 minus 8 is 4. An even number minus an odd number is odd. 12 minus 9 is 3. Now, they're concerned about this use of numbers. Now, this is where we have to focus on numbers for this story I'm telling now. If a square has an even number, then its side is an even number. So 16 is a square number, 4 squared, and its side is 4. 36 is a square number, and its side is 6. 6 times 6 is 36. Now, if a square is double or half of another square, then both squares have even numbers and consequently sides with even numbers. That is, if they're divisible by or multiplied by 2, then the square number is even, and so is the side. And conversely, if a square has an odd number, then its side is an odd number. So 25 is a square number, and its side is 5. 5 squared is 25. And 9 is a square number, and its side is 3. 3 squared is 9. All right. Now, Aristotle in the Prior Analytics tells us that if the side and the diameter are assumed commensurable with each other, one may deduce that odd numbers equal even numbers, and this contradiction affirms the incommensurability of given magnitudes. Now, we have a proof that looks very similar to this, preserved in Euclid in Book 10, the one on irrationals, incommensurables. And it was originally in Book 10, Theorem 117. But Heiberg in the 1880s, who produced the great review and organization of Euclid, believed that this belongs to a later period. And so he took it out and he put it in Appendix 27, in Appendix 10 to Book 10, Theorem 27. When the great mathematician Thomas Heath in the 1920s, 30s, who does an English translation and commentary based on Heiberg's text, he produced, and this appears in his Manual of Greek Mathematics and also his History of Greek Geometry, the same proof. Now, here's how he thinks the proof lays out. Suppose he says the diagonal AC of a square to be commensurable with AB its side. That is, this AC, diagonal of this square, is commensurable with side AB. And let A and B, alpha and beta, be their ratio expressed in the least possible numbers. So since we can see that AC, the diagonal, is longer than AB, and if we call AB 1 unit, then AC has to be greater than 1. Therefore, alpha is greater than beta, and therefore alpha is necessarily greater than 1. That is, this is greater than this. This is 1, this is greater than 1. Now, AC is to AB as alpha is to beta. But now we have the Pythagorean theorem. And since AC equals 2AB squared, that is, the square on AC is twice the square of this. This has 2 pieces. This has 4 pieces. Then A squared equals 2B squared, dividing by 2. And so A squared, and therefore A is even, because A has a value divided by 2. Now, since alpha to beta is a ratio in the lowest terms, it follows that B must be odd, right? It can't be even, because then it would be further divisible if both alpha and beta are even. Now, by substitution, which I'll explain in just a moment, let alpha equals 2y, and therefore 4y squared equals 2b squared, or 2y squared equals b squared. Now the value of b is going to be multiplied by 2, so that b squared, and therefore b is even. But b was also odd, which is impossible. Therefore, the diagonal AC cannot be commensurable with the side AB. Now, it's been my continuing argument, in accord with Sabbatai Unguru, the mathematician and specialist in ancient Greek mathematics, and against Neugebauer and van der Waorden and Oscar Obo, that the Greeks did not have geometric algebra, and that since the Greeks didn't have algebra, trying to make clear what they were doing by appeal to algebra is perfectly misleading. So now let's take a look at what the argument looks like, as I do in physics of the Pythagorean theorem, geometrically. So we're going to start with the same diagram, and we're going to ask whether AC is commensurable or incommensurable with side AB. And we have these pieces, AB, and then we have 2 numbers. The numbers are EZ and H. Now, that means I've got a square AB, CD, and then the square on the diagonal, which is twice the size. Then I'm going to ask us to imagine, as the proof goes, a number EZ, which is going to be to H, as AC is to AB. And then we're going to cut EZ in half at theta, and imagine E theta and its relation to here, to the square on E zeta. So it's manifest that the square on AC is double that on AB. And so what we've said is that since AC has to be greater than AB, if you think AB is 1, then the ratio of AC to AB must be the same ratio. He's going to go on to argue that AC has to be greater than 1. And now if we're going to call that number EZ, and its relation to H is going to be the same as AC is to AB. Now we're going to let this be divided here, E theta, in half, so that, let it be divided so that EZ and H are in the least possible number of having the ratio, and they're relatively prime. And EZ is relatively prime, so H has got to be odd, because if H was not odd, then it was even, and this is even, then they'd both be divisible by 2, and so they wouldn't be the least possible numbers of that ratio. And so H can't be even. But now, here's the problem. Since EZ is the double of E theta, the square on EZ is 4 times the square on E theta. But the square on EZ is already is double that of H. So the square on H is double that of E theta. So that if the square on EZ is double that on H, so the square on H is double that on E theta, so the square on H has got to be even because it's twice this size. It's times 2. And therefore, if the square on H is even, then H is got to be even. But we already insisted that H has to be odd if it's in the lowest common denominators with EZ, which is impossible. And so AC is incommensurable with AB, and that was what was meant to be proved. And I'd like to make clear why, on this view, the Pythagorean theorem is supposed that if the square on AC is double that on AB, that means that the square on AC equals the square on AB plus the square on AB. This form of the theorem is all that is needed here. Now, I'd also like you to understand this idea that EZ and H are numbers, though it looks like they're geometrical line lengths. So please follow this very important point. If these lines were commensurable, then each could be viewed as representing a number. And that is the given square. Now, it so happens that the double of the given square that the problem in the Mino is to figure out the length of a line that would give a square double the size of the given square that ABCD. We're going to use different letters now. So the problem isn't the same to discovering commensurability. But here's what the argument is that's proposed by Wilbur Noor. Let's start with this square, ABCD. Now, we're going to make a square on it, and the problem is to show Noor thinks that DB is incommensurable with its diameter DH. So what he's going to do is he's going to make another bigger structure around it. Now, please notice that in this bigger square, AGFE, we have 1, 2, 3, 4, 5, 6, 7, 8 equilateral triangles, isosceles right triangles. And in this one, we have 4 isosceles right triangles, and in this one too. Now, the argument or line of reasoning is this. If this square is twice the size of this square, then this square has to have an even number, and therefore side AG has to be even. And if this square is twice the size of this square, then this square has to have an even square number, and hence the side DB is even. And if that's the case, then this square, which is 1/4 the size of this bigger square, is divisible by 4. And this square has to be even. And so in every case, although the supposition is that the relation of the diameter DH is to DB, so that DB is 1 unit and DH is a number that's greater than 1, and then we ask, how many lengths of DB can measure DH? The answer is there's always, it's something greater than DC, but not a DH, and it will always leave a remainder. And that means that in this case, this diameter and this side will be even though the supposition is that one's odd. And so Noor thinks that the procedure of understanding how they reasoned that the diameter was incommensurable with the side followed that line of reasoning, which didn't require a knowledge of the Pythagorean theorem. And Noor places the discovery between 430 and 410 BCE. He places it among the latest of the specialists in ancient mathematics. So now let me turn to the third theory, and that is this. Hippasus, who's credited with, Hippasus published the discovery of both incommensurability or irrationality, same term, it's asumetron. We have it on the one hand, and of the dodecahedron inscribed in a sphere, and he perished at sea. And that's the point of view of what he thinks Panchenko has argued we can agree to about the conflicting evidence about Hippasus. I share Panchenko's view, also shared by Jmud, and Leonard Jmud had also argued that Hippasus belongs to a period around 500 BCE, and that's a point of view I am accepting by the most recent arguments by Panchenko and Jmud. Now, there's no other candidate except for Hippasus or Pythagoras for this discovery, and I think it's clear that this discovery can't be credited to Pythagoras. But let's take a look at how the investigation of the dodecahedron from the regular pentagon might have suggested incommensurability. And before I get there, let me just emphasize this point, that Proclus has a passage in which Pythagoras is credited both with the discovery of the irrational and the construction of the regular figures, the tetrahedron, the octahedron, the icosahedron, the hexagon, and the dodecahedron. And what editors have done is to amend Proclus's text to say Pythagoras is connected to the theory of proportions, that is, as opposed to the theory of irrational, and to the construction of the regular solids. And Panchenko thinks that both of them, in fact, properly belong to Hippasus. It's a very clever suggestion. In order to understand how this whole argument could have worked, we're going to look at antiphoresis. Now, antiphoresis is a transliteration of the Greek term antiphyresis, formed from uvaireo, to subtract, and anti, whose meaning here is mutual or alternating. And so antiphyresis is often translated as mutual subtraction. It's a generalization to magnitudes of the so-called Euclid algorithm used to determine common measure, literally the koinon metron, the greatest common, or spoken of as the greatest common divisor. Now, I'm only going to stop on this for a second, but in Euclid's book 7, theorems 1 and 2, take a look at book 2, proposition 2, to find the greatest common measure, the koinon metron, of given two numbers, and that is this procedure of antiphyresis. Now, so I can explain briefly what this procedure is, and then I'll tell you why I'm saying this, is let's imagine we wanted to cut this circle or this pie into 9 pieces. We take our compass and open it to 1/9, and then we go and we try to make these black lines along the circumference, and so on. Now, let's say after making those, we see that we still have a remainder left over. Then by I, we divide this into 9 equal pieces. Then we open our compass 1/9 more, and then we go and make the lines again and then cut the pie. Now, if the first attempt of the division into 9 parts gives something more, not less, we can also divide the small part into 9 parts and decrease the opening of the compass by antiphyresis, by mutual subtraction. Now, here's where I'm asking my audience for help. Von Fritz in the 1945 article, mentioned that the practice of mutual subtraction was routinely used in the crafts. To know the ratio between two straight lines, says von Fritz, the method was an old one known to craftsmen as a rule of thumb to find the common measure with measuring sticks and ropes. If anybody's hearing this presentation and can tell me other crafts that have made use of antiphyresis, please let me know. I'm at hanrobert@hotmail.com, and I'm eager to hear any suggestions. Now, let me show you how this would work by looking at the regular pentagon, of which 12 of them put together will fold up into a dodecahedron, which is going to be the hole into which the four elements are then placed. So first, let's take a look at drawing the diagrams inside of a regular pentagon, five-sided figure. Notice we do these diagrams, and lo and behold, there's an isosceles triangle inside a regular pentagon. Make another diameter, and you can see now here's another isosceles triangle inside. Make another diameter, and there is another regular isosceles triangle inside, and yet one more. So the regular pentagon has inside of it isosceles triangles. Now, you can also notice this, that inside this regular pentagon, when you make the diameters, a regular pentagram, you have another regular pentagon inscribed, which is now upside down. Here's the point on top, there's the point on the bottom. And if you'll now make these diameters inside, you'll see that there's another regular pentagon inside them. Here is now right side up. This was right side up. This is upside down. This is right side up. And if you'll keep on making the diameters inside a regular pentagram, inside a regular pentagon, you will produce another regular pentagon inside. Make the diameters, you'll have another regular pentagon inside ad infinitum. Now, what we want to know is what's the relation between the diameter and the side of a regular pentagon. Now, please note that the triangle AED, A and D, and A and E are equal length because this is an isosceles triangle. So while I want to compare AB to AD, I can use this length to compare them. It's the same length. AD is the same length as AE. So if I take length AB and I subtract AE, I'm left with the red remainder, BE. Now, it's going to turn out that this remainder, BE, is not only equal to AF, but is equal in length to FG. So if you take this length, AB, and you subtract the side, mutual subtraction, antiphyresis, AE, your remainder, BE, is the diameter of the next pentagon inside. And now we ask, what's the relation between this FG and its side FE? What's the relation between FG and FE? And the answer is going to be that FG minus the side FH yields a remainder HK, which is the diameter of the next smaller pentagon. And when you compare the length of this diameter with its side, you're going to get a remainder of the next smaller pentagon inside ad infinitum. So subtracting FE from the diameter FG leaves the remainder GH, which is equal in length to the diameter of the next smaller pentagon HK. And this process goes on forever. Thus, the sides and the diameter of the pentagon must be incommensurable. The sequence of quotients in this case, derived from the process of antiphyresis, is 1, 1, 1, 1, 1. Not meaning that the remainder is always 1, but that at each step, the remainder measures the divisor only once before leaving the next remainder. So here is the point I'm driving at of what happened as Hippasus is looking at it. I'm arguing he's searching for the common measure. And in the search for the common measure of the diameter and the side of a regular pentagon by mutual subtraction of the side from the diameter, the remainder will always be the diameter of the next smaller pentagon. By subtracting the side of the next smaller pentagon from its diameter, the remainder measures the divisor only once before leaving the next remainder ad infinitum. So let me emphasize now, as I'm trying to wrap up this presentation, finding the common measure is part of the search of the early Greek philosophers to search for the module. So let's resituate Hippasus' investigation in the context of Aristotle's report that the earlier philosophers, such as Hippasus, were substance monists. Hippasus is included along with Aristotle, with Heraclitus, holding that fire was the underlying substrate that altered without changing. That's what Aristotle claims, because it never perished. The exploration of the dodecahedron, in terms of its constituent part, the regular pentagon, needs to be reset within the context of the metaphysical context. So in the 6th century BC, the Ionic temple architects had a module in terms of which they made the whole building, and the module was column diameter, lower diameter. And so the height of the column, the size of the column capital, the architrave, the geison, the Pima, the frieze, the pediment, all were calculated, including the layout of the floor plan and the distance between the columns in terms of the module. Anaximander adopts a modular technique, and moreover, he adapts the architect's module. Anaximander measures the cosmos by the module of or common measure of column diameter. He likens the size and shape of the Earth to a 3x1 column drum and measures out the distances to the stars, moon, and sun in earthly, that's column drum diameters. And I discussed this in my book, Anaximander and the Architects, and also have discussed this in subsequent books, Anaximander in Context, and in Archaeology and the Origins of Philosophy. When Thales measures the height of the pyramid when the shadow equals the height, or when the shadow is unequal in height, or measures the distance to a ship at sea, he's using a gnomon. And when Anaximander made a seasonal sundial, he has a gnomon, and that he measures the local noon shadows. And the shortest of all the local noon shadows is the summer solstice. The longest of all the local noon shadows is the winter solstice. And the equinox is not midway between, but it's on this line. Thus, both Thales and Anaximander made use of a gnomon as module or common measure. The gnomon size remains the same, and only the shadows vary. Then coinage is introduced in Lydia and embraced in Miletus and in Ionia. Here we have a stater that's roughly 14 grams, and then that's the module. And this is the half stater, this is the 1/12 stater, and this is the Tarte Morion, or 196 stater. All of them are multiples or subsequently submultiples of the stater. Coinage introduced a new module or common measure in terms of which all other things can be assessed and evaluated. The stater remained the same, and all other denominations were multiples or submultiples. Now, Heraclitus has testimony that shows he was also a modular thinker. He says all things are an interchange for fire, and fire for all things, just as goods for gold and gold for goods. So fire is the substance monism by analogy with the module of coinage. The 6th century BCE philosophers, surrounded by examples of modules or common measures, and interpenetrating their thoughts, it's my thesis, they inferred a metaphysical module by analogy with them. Thales called it water, Anaximenes air, Heraclitus fire. Then Thales, and in turn Pythagoras and the Pythagoreans, explore geometry to work out its modular structure. Now, here's the question of the missing context in the reviewing the Greek discovery of incommensurability. What prompted Hippasus to explore this geometrical figure, the regular pentagon? So let me then wrap up by drawing your attention to the problem of incommensurability in the big picture. The early philosophers were seeking the persistent one under many, the module or common measure. That's what Aristotle tells us, and I think his report is spot on. The right triangle is the fundamental geometrical figure. This discovery, the right triangle being the fundamental geometrical figure, was displayed in the Pythagorean theorem along the lines that led to what was preserved in Euclid, Book 631, by similar right triangles. The application of Area's theorem was the next contribution by Pythagoras and the Pythagoreans, which was to transform triangles into rectangles, parallelograms, and figures of different shapes to account for the diversity of appearances from the right triangle. This is all part of building the cosmos out of right triangles. And next, the systasis, or putting together of the regular solids, the building blocks or molecules made from right triangles. The construction of the cosmos from right triangles, the right triangle is the module. And so just to sum it up here, so the lines of the Pythagorean theorem, there are more than 350 proofs. The Greeks show us they knew two. One is preserved in Book 1 of Euclid, Theorem 47. The other is in Book 6, Theorem 31. You can see that the square on the hypotenuse of a right triangle is equal to this rectangle. And the square on AB of that right triangle, the hypotenuse of that right triangle, is equal to that rectangle. And hence, the square on the hypotenuse is equal to the sum of the two squares. And it had to be shown empirically for the scalene right triangle. The next step was to show the application of Area's theorem, that from a triangle in any angle, you could then make a parallelogram attached to BC, which was equal in area to the triangle. Then take any other figure, divide it into triangles, and then attach to BC a parallelogram that's equal in area to this figure. Then take line BC and CF and find the geometric mean between them, which is GH. And on GH, make a triangle that is similar to this triangle and equal in area to this. How it is, they were searching for a way to explain how from triangles, all the other figures in the world, volumes and all the other volumes or bodies built out of surfaces or bordered by surfaces were constructed. And here's the systasis of the regular solids, figuring how many equilateral triangles, 3, 4, and 5, 3 squares or 3 pentagons will fold up in order to make these basic elements. And then this is fire, air, water, earth, and then the dodecahedron made from these regular pentagons, which was the sphere or the hole, looks like a soccer ball, into which all the elements were fitted. Conclusion, Hippasus plausibly discovered, visualized incommensurability while exploring the regular pentagon, the building block of the dodecahedron. He was looking for the common measure or module of the figure. His discovery was part of the project taken up by Pythagoras, Pythagoreans, bequeathed by Thales, searching for the structural building block of the underlying unity that alters without changing. Hippasus, according to Aristotle, thought it was fire, not water, as Thales posited. We need to resituate Hippasus's discovery of incommensurability within the broader metaphysical project to see his visualization and discovery. Thank you for your attention.